In this video, I will show you how to approximate the area under a curve using the different types of Riemann sums. I will also show you how to tell if you are getting an overestimate or an underestimate. Number 1. Approximate the area under the graph of y equals x squared on the closed interval from 1 to 9 using two subintervals of equal width and a midpoint rectangular approximation, or RRAM. Because this is a review video, I won't be going into as much detail as I did when I first taught this topic. So if you need a more detailed explanation, I will try to put a link up here in the upper right hand corner. We are given the interval from 1 to 9, and we are told to separate this into two subintervals of equal width. Notice that 1 and 9 are 8 units apart. So our two subintervals should each be 4 units. So how about a subinterval from 1 to 5 and then 5 to 9? That will make each subinterval 4 units wide. For this method, we need the midpoint of each interval. So the midpoint of 1 and 5 is 3, and the midpoint between 5 and 9 is 7. The idea of midpoint rectangular approximation is that we are using two rectangles to estimate the area under this curve between 1 and 9. Each rectangle will touch the graph of y equals x squared right at the midpoint of the rectangle. So this is the intersection point because the midpoint right here is 3. And we'll have another rectangle like this, and again the midpoint of the rectangle should meet the curve. So we have a midpoint right here, and this midpoint is at 7. We know that the area of a rectangle is base times height, so we will need the base of each rectangle. The base of the rectangle is the width of the subinterval. In each case, that's going to be 4. So the first rectangle has a base of 4, and so does the second rectangle. All we need now is the height of each rectangle. Well, the height of the first rectangle will be the value of y equals x squared at x equals 3. So this is going to be y at 3, which is going to be 3 squared, which equals 9. So the height of this first rectangle is 9. Similarly, the height of the second rectangle will be the value of y equals x squared at x equals 7. So that's going to be y at 7, which equals 7 squared. So that's going to be 49. The sum of the areas of these two rectangles will be our approximation of the area under the curve between 1 and 9. So our area approximation is going to be the base times the height of each rectangle added up. So for the first rectangle, the base times height is 4 times 9. And then for the second rectangle, base times height is 4 times 49. And this is a perfectly acceptable answer for a Riemann sum. But this also simplifies to an area of 232. Problem number 2. Determine whether each approximation will be an underestimate or an overestimate of the true area. Circle one answer per row. By the way, LRAM stands for Left Rectangle Approximation Method. We saw that MRAM stood for Midpoint Rectangle Approximation Method, and you can probably guess that RRAM stands for Right Rectangle Approximation Method. TSAM stands for Trapezoidal Sum Approximation Method. I want you to memorize the following facts. The left and right rectangle methods will either give you an overestimate or an underestimate depending on whether the function is increasing or decreasing. The other methods, RRAM and TSAM, will give you an over or underestimate depending on whether the function is concave up or concave down. So here again, for LRAM and RRAM, it depends on whether the function is increasing or decreasing. For MRAM and TSAM, it depends on the concavity of the function. To answer these questions, you need to have some knowledge of what the parent functions look like. For part A, let's not start with e to the negative x power. Let's start with the true parent function, y equals e to the x power. You should have memorized that this function looks like this. It's an increasing exponential function. But if you take this and you turn it into e to the negative x power, this is a reflection over the y-axis. So this whole thing is going to flip backwards. So this is going to be a decreasing function. To decide if this will be an underestimate or an overestimate, let's do a little sketch. Left rectangle approximation means that when you draw your rectangle, the left edge of the rectangle should touch the function. So you get a picture like this. Remember that we are using rectangles like this one to approximate the area under the curve. But in an LRAM situation where the function is decreasing, the rectangles include this extra area that is above the curve. So we get an overestimate. Part B, we have memorized that y equals sine x looks like this. It starts at the origin, it goes up, then comes back down to the midline, then it goes down, and then comes back up to the midline, and then repeats. However, we are only being asked about the area under the curve between 0 and pi over 2. So let's look at that again. Pi over 2 would be this first mark right here. So the sine function just going to pi over 2 is looking like this. MRAM is midpoint rectangle approximation. So I've drawn a rectangle so that the midpoint is touching the function. It's hard to tell from this picture whether it's an underestimate or an overestimate because the rectangle includes a little bit that is above the curve, but it's also missing some that is below the curve. So which is it? Here's a trick that you can use. I have memorized that MRAM and TSAM are opposites when it comes to underestimate and overestimate. So I like to draw a TSAM picture, a trapezoid picture, and I can easily see that this is an underestimate because I see all of this area under the curve that's being left out by this trapezoid. So if the TSAM gives me an underestimate, that means MRAM will be an overestimate. For part C, you need to reach way back into your pre-calculus knowledge and hopefully remember that tangent has a period of pi, and tangent always begins and ends on the x-axis, and there is an asymptote right in the middle. So there will be an asymptote right here. And then from left to right, the tangent function is always increasing. So it's going to increase as it approaches the asymptote like this, and then on the other side, it's increasing as it approaches the midline. For this particular problem, we want the area under the tangent curve from 0 to pi over 3. So here's pi over 2 right here. So pi over 3 will be somewhere short of that. So this is the area that we're trying to approximate right in here. Right rectangle approximation means that the right edge of the rectangle is touching the function. This will give us an overestimate because we can see that the rectangle includes all of this area that's actually above the curve, not below. So overestimate. Hopefully you have memorized that the natural log curve looks like this. Since this is TSAM, we use a sideways trapezoid to approximate the area under the curve. But we can see that this little area under the curve is being left out by the trapezoid. So we have an underestimate. Number 3. G is an increasing concave up function with values given in this table. Approximate the area under the graph of G on the interval from 0 to 9 using a right rectangle approximation method, or RRAM, and the 3 subintervals indicated in the table. Here is a right rectangle model to help you visualize what we are doing. Notice that I've drawn the rectangle so that the right edge of the rectangle just touches the function. These subintervals will come from these x values. So we have an interval from 0 to 1, and then another interval from 1 to 4, and another interval from 4 to 9. The base of the first rectangle will just be the width of the interval. So from 0 to 1, that's 1 unit. Similarly, the second rectangle has a width of 3 units, and 9 minus 4 is 5, so that's the base of the third rectangle. The height of the first rectangle will be the value of the function at 1. So the value of the function at 1 is 2. The height of the second rectangle will be the value of the function at 4. The value of the function at 4 is 8. And similarly for the last rectangle, the height will be the value of the function at 9. And that's 18. The area approximation will be the sum of the areas of these 3 rectangles. So for the first rectangle, base times height is 1 times 2. And then the second rectangle, we have 3 times 8. And for the third rectangle, we have 5 times 18. For a free response question, you can just leave your answer like this. But just in case we have a multiple choice question, the area is 116. Number 4, is this approximation more or less than the exact area of the region described? Give a reason for your answer. We can tell from our right rectangle model that this is giving us an overestimate because of the way the rectangle includes a portion of area that is above the curve. However, your justification must be based on these facts that I asked you to memorize. RRAM will give you an overestimate or an underestimate depending on whether the curve is increasing or decreasing. In the setup, we are told that the function g is increasing, so we will mention this in the justification. So we can say more because g of x is increasing. RRAM gives an overestimate of the area of an increasing function. Number 5. Approximate the area under the graph of G on the interval from 0 to 9 using trapezoidal sum, TSAM, and the 3 subintervals indicated in the table. We are using the same intervals as we did before. Here's a trapezoid model to help you visualize what we are doing. Notice that a trapezoid has 2 bases. There's one here and then there's one here. This is sort of a sideways trapezoid from what you're used to. So that's why I'm going to include 2 bases for each trapezoid on this chart. Let's start with the interval from 0 to 1. This first base is going to be the value of the function at 0. The value of g at 0 is 1. The second base will be the value of g at 1. That's 2. The height of the trapezoid is the distance between the bases. In other words, the width of the interval. So the height of the first trapezoid is 1. Moving on to the second trapezoid, the first base will be the value of g at 1, which is 2. The second base will be the value of g at 4. That's 8. The height will be the width of the interval. That's 3. And then again for the third trapezoid, base 1 will be the value of g at 4, which is 8. And base 2 will be the value of g at 9, which is 18. And the height of the trapezoid will be the width of the interval, which is 5. Remember that the formula for the area of a trapezoid is 1/2 base 1 plus base 2 times height. So our area approximation will be the sum of 3 trapezoid areas. So we're going to have 1/2 base 1 plus base 2 times the height, plus another 1/2 base 1 plus base 2 times the height. And then one more 1/2 base 1 plus base 2 times the height. You could leave your answer like this. Very often you will see the first part of each term simplified. So in this case we have area equals 1 plus 2 is 3. Half of 3 is 3 over 2. So you might see the first term written as 3 over 2 times 1. Similarly, we have 2 plus 8, that's 10. Half of 10 is 5. So that's going to be 5 times 3. And then 18 plus 8 is going to be 26. Half of 26 is 13. So 13 times 5. If you added up all of these products, you would get 81.5. Number 6, is this approximation more or less than the exact area of the region described? Give a reason for your answer. We can tell from the trapezoid model that this is going to give an overestimate. Alright, we are including more area than the exact area described. However, your justification must come from this set of facts that I have asked you to memorize. For TSAM, you will get an overestimate or an underestimate depending on the concavity of the function. We were told in the setup that function g is concave up, so we must mention this in our justification. So, is the approximation more or less than the exact area of the region described? More, because g of x is concave up. TSAM gives an overestimate for the area of a function that is concave up.